喂，好。Last time we talked about adsorption, and there are two classes for adsorption. The first one is molecular adsorption, and we have derived the equation and draw two plots for the molecular adsorption last time. So today I introduce you the atomic adsorption. Okay, the other type of adsorption. And we will derive the equation and we will draw two plots as well. So please go to slide 38. Slide 38, the objective is carbon monoxide. Again, carbon monoxide, but it is atomic adsorption, so we need two active sites. The carbon and the oxygen will adsorb on active site separately. Okay, and there are some retreatment for this one. The first one is there should be two active sites, right? And for these two active sites, it should be adjacent. So that means if there are several active sites, here, but if you want to do the atomic adsorption, C and O should be adsorbed on adjacent active site. Okay, so it cannot be like this. The active site should be adjacent. That is the first requirement. Okay. And what is the probability for two vacant sites occurring adjacent to one another? So that means if there are four active sites, and you choose two randomly you choose two, what is the probability for adjacent sites? Okay, so the probability is proportional, like if you choose this one or this one or this one, okay? The probability is proportional to the vacant site concentration square. It is a matter of mass, okay? So I don't want to talk a lot about the probability. So you randomly pick two. The probability is for the adjacent two is proportional to the vacant site concentration square. And also we know the adsorption rate is proportional to the pressure of reactant. Therefore, for this case, the adsorption rate is proportional to the pressure of carbon monoxide and the vacant site concentration square. That is the conclusion here. you can compare this one if you want to compare this one with the previous one. This one is for the second case, right? Atomic adsorption. Do you remember what is the equation for molecular adsorption? For case 1, okay. I just want to review. For case 1, the previous case, the adsorption rate is proportional to this one, okay? The previous one, you can compare. So for the molecular adsorption, the previous one, the rate is proportional to pressure and the active site concentration. Vacant site concentration. But for the atomic adsorption, the rate is proportional to the pressure and the square. The different part is the square. Because the vacant site should be adjacent. It is a matter of probability. Okay, so based on this one, let's try to derive the equation. Okay, let me modify something. Okay, if you remember, we talked about adsorption, but you have to think about the attachment and the detachment, right? So for this one, let me modify something. This one is attachment. Okay? Attachment. So maybe you can modify this thing. The attachment rate is proportional to pressure and the vacant site concentration square. Attachment. Because at the next slide, I will talk about detachment. So please modify. I think I put some wrong word later. At slide 39, okay, 39, the first two letters, please modify this one, as detachment. It is better to understand. Okay, so now we talk about adsorption. For the adsorption process, there are two actions, attachment and detachment. For attachment, it is proportional to pressure and the vacant site concentration square. Okay, so we have finished this one. Attachment is proportional to pressure and vacant site concentration square, right? How about the detachment? The detachment, you can see the slide 39. Two occupied sites must be adjacent. Okay, and the detachment rate is proportional to the concentration of CS and the concentration of OS. Okay, so that means more CS and more OS, the detachment rate will be higher. Okay, so the detachment rate is proportional to the product of the occupied site concentration. So it is proportional to CS, concentration of CS, multiply concentration of OS. Okay, proportional to the product of these two. So now we got these two. And you can represent this one as concentration CS and concentration OS. Okay, it will be more clear. Concentration CS, concentration OS, and this means the they occupy the side of CS, occupy the side of OS. But this one may be more clear for you, the concentration for these two. Okay, so by sum up of these two, the assumption, attachment and detachment. So actually for this case, the net rate of the adsorption for the atomic adsorption, for the second case, atomic adsorption, rate of the adsorption, okay, rate of the adsorption equals to attachment rate minus detachment rate, okay? And the attachment rate is proportional to the pressure and the vacant site concentration square, right? But now it is an equal sign, so we have to put a constant here. So that is Ka. So this one is for attachment, okay? And then minus detachment. The detachment is proportional to concentration of CS and the concentration of OS. Again, here it is an equal sign, so we should put a constant here. Okay, so that is the net rate of adsorption. You can write down at the middle of slide 39. Okay, how about the bottom one? So next, the equation. If you remember, next we will put the equilibrium constant. So the equation for dissociative adsorption. Associative adsorption. So actually this is the atomic adsorption as well. So we modify this one. Okay, let's modify this one by introducing the equilibrium constant. So RAD can be write down using another expression. So we bring Ka out of the equation. So pressure, vacant site concentration square. And then this should be the equilibrium constant, the capital K. Okay, and you can remind yourself again, Ka equilibrium constant, Ka equals to the forward rate constant over reverse rate constant. Okay, so we can rearrange this one into that one. So we will draw two pictures. We will draw two plots for this case by using the second equation. Okay, so let's continue. Next slide. Slide 40. Let's derive the equation at slide 40. So first at equilibrium. We discuss this by at equilibrium condition. Okay, so at equilibrium, that means the forward and the reverse reaction rate is almost the same. So at equilibrium, the absorption rate equals to 0, right? At equilibrium, the forward and the reverse reaction rate are almost the same. So this one is this one, right? They are the same. So at equilibrium, it is equal to 0. So this one equals to 0. This one equals to 0. So this one equals to this one, right? So PCO CV squared. Right? And which one do you want? Do you remember the purpose? Do you remember the do you remember what is the picture we want to draw? Isostar, right? Remember? We want to isostar. So for this case, you don't have to draw this now. I just want to mention. So finally, we want the pressure versus concentration. Okay? You can check for the previous case. In the previous one, we have this figure, right? At slide 36, we have this one, okay? So now, we want this one, or this one, okay? Because the COS equals to CCS. Originally, we got this one, right? Right? It is the chemical reaction at the beginning. So we have CO. So the amount of CS and OS is the same. So you can draw this one or you can draw this one. Okay. So next, how to rearrange this one? What is the parameter you want? Yeah. Because you have to draw the plot, so I want to do this, okay? I want to do this. And please also use this one, okay? This one is from RAD equals to 0. This is RAD, so we got this one, okay? And then you have to know this one. Because we have 1C, 1O together. So CCS equals to COS. So now, what is COS? Right? They are the same. So it is like COS squared, and you multiply this one here, you have the square root, then you can get this one. So now you have COS and the PCO, right? COS and the PCO. That is the X and the Y axis. Okay, so can you draw a figure using this equation? What is the unknown, or there is no unknown? So you can check It is x. It is y. It is a constant, right? Constant is okay. How about this one? This is unknown. So similarly, again, we have to replace CV. We have to replace CV. So second one, please use site balance. The same, right? The same as the previous one. So site balance. Site balance is our total CT, total concentration, equals to vacant site concentration, and CS and COS. Okay, and let's replace these two. Replace these two using this one. Okay, so let me replace CV, that one, the same one, okay, and we want CV, right? We want CV, so what is CV? What is CV? CT over okay, we got a CV here. Any question? Okay, so we got a CV. Finally, you can bring CV back to this equation. So bring the CV in second one into the first one. Okay, bring the CV in second one into the equation in first one. Then you can obtain and then we can draw the picture. 如果你40页有看到一张图，你先不要理它，我不确定我有没有改。40页如果我画好，没有好，那就好。Okay, so let's use this one. Is that okay? This one is x, right? PCO x. COS is y. Constant. Okay, so we can use this one to draw the isotherm. Okay, so again, how to draw the isotherm? We divide the region into two parts, the large P or small p. Large P or small p. So first at large PCO. We use the same technique, okay? Large PCO, we compare this one. If PCO is large, that means the relation, right? The relation for length. Okay? So, COS equals to, you can ignore 1 at the bottom. Okay? And we can delete these two. I think if we start at a small PCO, maybe easier to draw the curve, but it is okay. Large PCO, okay, then small PCO. For small PCO, 1 is larger. So COS right? So it is proportional to this one, okay? So do you know what is the curve for this one? If y is proportional to square root of x, what is the curve? Do you know? It is parabolic. So it is like this one. Parabola, 抛物线. You may be more familiar with when you are in your junior high school. I think maybe you have learned this, right? The first curve. It is like this. And if you change these two, like this, the curve will be like this. Okay, will be like this. And if you have a square, okay, if you have a square, this is that one, right? And the square root of x is larger than 0, then you got this one, like this one. And also, maybe you can indicate it this as CT over 2. The value here is CT over 2. Okay, so that is the isotherm for dissociative adsorption or atomic adsorption. Isotherm. So you do the experiment, you got the data, and you use the data to draw the isotherm. You can observe your isotherm and decide what is the behavior for your experiment. Okay, so you can compare. I just want to compare the previous one for you. Your figure may be at slide 36. You can compare the molecular adsorption or non-dissociative adsorption. Isotherm. So we divide it into 2 parts as well. At a large PCO, it is a constant, but it is CT. It is CT. And the small PCO, we have a linear. It is a linear plot, but it is parabolic plot. Here. So you have to tell the difference. Molecular adsorption. Molecular adsorption. Atomic adsorption. We still have one figure to draw. Okay, so let's modify the equation. Start from here, okay? Let's modify the equation. So you can go to slide 42. We take 2 steps. First one, we take inverse of both sides, okay? Inverse of both sides. So what is the inverse of both sides? Right? Inverse of both sides. And then multiply PCO square root at both sides. So PCO 2.5 and this one, right? And I want to further modify this one by separate them into 2 terms. The first term and the second term. You can check. Please check by yourself, not just writing. So what is the x, what is the y? Okay, so now we choose this one as y, and then we choose this one as x. Okay, so let's have another figure. So XPCO square root, and okay, so for this one, we got a line, and maybe you can do have an intersection, and the slope of this line 2 over ct. The x intersection here, y intersection is this one. Okay, let me copy the previous one for you. So again, you can compare. They are a little bit different, right? So this one is the second case, atomic adsorption. And this one is the first case, molecular adsorption. Okay, so what's the function for these two? That means if you draw you have two choices, right? If you draw this one, y versus x, or you draw this one, y versus x, and you can see which one you can get a linear line. You can get a line. Which one is more like a line? That means the behavior of your experiment is more like atomic or molecular. So please understand how to derive the equation and how to use the equation to plot these two figures, okay? And how to tell the difference between atomic and molecular adsorption. That is the adsorption part. I want to talk a little bit about the next one, surface reaction. So adsorption is the step 3, right? Step 3. And now, step 4. Step 4, surface reaction. Okay, so previously, at the slide 43, previously, we have achieved this step, right? This one is adsorption. Okay, previously, step 3, at step 3, we have done this. Okay, so now for adsorption, for surface reaction. For surface reaction, CS becomes BS. Okay, so now we talk about this one at this section. We talk about this one. There are several behaviors. Let's go through this briefly. Okay, you can see the first one. Single site, alright, single site reaction. The next slide, dual site reaction, dual site. And you can see slide 47. Henry Rindell, it is the additional type for the surface reaction. So let's see the first one. I can only finish this one. Single site surface reaction. Okay, so single site reaction means AS becomes BS. So that means you can see a figure here. Alumina is the catalyst, okay? Alumina is a catalyst. So single site. So previously, it is a normal one. Normal one. After reaction, iso 1. Isomerization, okay? You can see the example, right? So for this one, let's write down the reaction equation. There is a space, 左下角，好。Surface reaction, so the symbol is S, okay? Rate of surface reaction, RS, equals to, you just see this one, okay? You just see this one. The forward reaction, KS, CAS. Reverse reaction, K minus S and CBS. And we can rearrange by put the KS out of the bracket. And then use the equilibrium constant, capital S. Okay? So this one is the equation for single site surface reaction. We will talk about other behavior later, okay?